Dr. Franco, can you repeat?
No, I'm fine. You don't need to call me doctor every time if you.
Okay.
Franco is fine. Thanks. It's unusual to hear that. Okay. Let me.
We'll wait for another 3 minutes, then we can start.
Yes. Also seeing if the participants were able to log in. I think that will be the biggest challenge at the moment. Let's see.
We can record and stream this session,
Yes.
right?
Yes. Yes.
Okay.
This is available for everyone. For the participants that are in the session at the moment, can someone give feedback if you are able to, let's say, log in, or did you have any trouble getting the link to AVR Web? Okay. Anyone? Just want to make sure that I'm showing something. People were able to log in.
Has anyone logged into the software, and can someone confirm?
Just,
Sachin, after we log in, it's saying your member request is waiting approval from the site owner.
sorry, that should have not happened.
Franco?
Yes. Yeah. Nothing that I can do because I'm not the site owner at the moment. So my colleague in the US actually told me, sent me an email in the morning that she cleared the cache and should be able to log in. Not sure if I can reach him now. Just check quickly, please.
I have received a mail which says that all the virtual demo machines are busy at the moment, so we are unable to provide you a link to try Aviva from the web at this time.
Yeah, that was the error message I got yesterday evening, but my colleague who is the site owner, who's taking care of all the accounts, sent me a message that he clears everything overnight and should be to go for today. That's why this message should not appear. Try to reach him. Second, please. I'm not sure if it's an I can go through the session, but then no one can participate because apparently no one can log in, despite they should be able to. That's why I tested it yesterday evening, and my colleague told me it would work. Just give me a second. I think
Franco,
he
if
might be
it's
online.
not available, then if you have the access to that open, then you can demonstrate. And since it's recorded and live streamed, people can try it later, as and when
Yes.
their links gets activated.
Yeah, that's a very good point. So we'll do it. Just so I wrote my colleague. He seems to be online. Just give me 1 or 2 more minutes. Maybe someone else is joining. If he's not replying, we just do what you just suggested. It's recorded. You can also provide my personal email address. I'll write it in the chat in just a second so that everyone, I apologize, just wants to have a private, it's called private session where we meet up on Teams or WebEx or separately, and I walk them through more, on a personal basis. I'm happy to do that because I apologize. It should work. So I'll post my email. I'm not sure if the users have access. So whoever wants to give it a try, just drop me an email. You make sure you have the link, or you get actually the full license, the full installable license to test, and then we repeat this in a different setting. It's just Leak seems to be online, but he's not responding. So have to wait until he's. Just let me check. Sorry, mistyped it. Things open. So disregard this email. Just there's an error in it.
Sure, Franco. Or else they can also mail to us and we will relay it to you. If
Yes. Yeah. So, so it's like a
anything is
microsystems,
fine.
not microscopy. Okay, perfect. We have lots of people, so probably everyone has the same error message then. But again, my colleague told me it would work. Apologies. And session is recorded. I'll start to share my screen. We go from there. If there are any questions, let me know. If you want to see something, also let me know.
Yeah.
One suggestion is for everyone is try after maybe 5 minutes. Sometimes it does give you access. It takes a while.
Yeah, so here we are relying on external provider, which is the Amazon services, but should be set up that it should all work. But sometimes, yeah, this can happen. So can everyone see my screen? I'm sharing my screen.
Yes, Franco, we can.
Perfect. Thank you very much. So if you have the link and you put in your credentials, it's opening up this one. So in your web browser, you would see the app stream version from the Amazon Web Service, and there you have Avia and something that's called CyberDuck. So you don't worry about the CyberDuck at the moment. CyberDuck helps us to link, let's say, Google Drive, OneDrive to these Amazon virtual machines so that we can upload data to this virtual machine and work on it. But we have already preloaded some data. So see the background. So let me start from scratch with that. If it opens up, the software, the AWS software, this is how it looks. I will go through the different parts of the software in a second. Please don't be overwhelmed with the software. But if this link works and you want to recopy it watching the YouTube videos, you should just go to Files, Open, and there we have a shared folder. So this folder is always there. It's created by us. It's part of the storage that we have there. And it has this demo data in there. And this is what I wanted to use today. You have also a temporary file folder and folder. This would be the folder where we can link Google Drive or OneDrive to it, upload the data, then it sits in here and you are able to open it. So let's say we go to the demo data. Those are different demo sets that we provide to you for practice, for working with the software before you maybe go into working with your own data. So let's say we want to look at the pixel classifier. We go to the pixel classifier demo set. You see there's already an image sitting in there. It's a TIFF file. It's an Avia TIFF file. So just click on it. You see it's asking you for the calibration. Don't worry about that at the moment. And it's opening the image up. So because we have already analyzed this image previously, there are also some results in this AVR-TIFF file. So we would take off those channels. Let me just restore the original one. Oh, the original view. Okay, so this would be the image that we have uploaded for you to do a bit of practice on the pixel classifier. But going through the software, how it looks, let me also show one thing before I go in full screen mode, because you see I'm still working from the browser, but I do this on purpose. Because on top of the software here, you have a search bar, and in the search bar, you can type whatever you're searching for in the software. So if you're not sure what the pixel classifier does, or what the recipe console is, or where I can store my image setting, just type it. It's kind of a search bar. Let's say we type in pixel classifier that we want to use. Go down here, it shows some YouTube videos that we have created explaining the pixel classifiers, as well as what's called, and it should open up in a second. It's opening up an additional browser in the browser. So it goes actually to the pixel classifier AVR wiki. This one, because it's up here. Sorry, can't see it. Open this one. So we have created a website instead of a handbook. So instead of sending you a PDF, maybe 200, 300 pages, in which we explain every single detail and part of the software, where to click, what is the parameter. We have created it virtually as a website, so it's interactable. So for example, you then come to the website for the pixel classifier. It's guiding you directly there. And here you can see a description of what is the pixel classifier, what are we using as, let's say, the features we are looking at, which class do they have, what are they doing. Another example, you have those demo sets that I showed before, so you could open them. You can read what in the protocol you can adjust, what are the parameters, what are the thresholds, which ones can be sent. And down here, you have even a tutorial to walk through the different steps of the software to come to the same result that is shown now in the software. Okay, so this really helps to learn the software and get familiar with. If you have no one explaining it to you, so just check the AVR, we call it AVR wiki, or the videos and the tutorials that we have there. So with that, that's enough to the search bar. And now I click on extending it. It's resizing. And now you should only see the software. Okay, so this is how you can use the software. This is running completely now on the Amazon Web Service. And I have opened the first image, which is a histology image. You can, with your mouse wheel, zoom in, zoom out. It is maybe more fluent if you do it, because I am also having the WebEx open and streaming at the same time I'm running the browser software. So on the left side up here, we see our image. We can zoom in, zoom out. We get some information displayed, like scale bar, what image does it, like what's the name of the image. And in other instances, we can customize what we see here. Okay. Below there, we have what's called the image explorer and image strip, and you see I have opened multiple data sets. This is a 2D, just one image, compared to, let's say, a 3D data set from neurons or Drosophila or a different cell. So whatever you open in the software, it puts it down here in the image explorer, and we can switch between the images very quickly. Let me click on it. On the right side, we have a channel setting. So every image that is open up, you see the channels that was recorded. Here you see actually 6 channels, but 3 of them we created using the pixel classifier and the machine learning. So I turned them off for now. If you click on this little eye, you can turn on and off. single channels, and can collapse it if you're done with your settings, or you expand, and you can click on each and single channel to expand and then play around with the histogram with just your channel settings. If you have done that, you can also go to, let's say, File, Export, and export your display settings. This creates an additional file to the original TIFF. So every time you open the TIFF, you can actually reload the settings you have done. So if you are changing the displays or the channel settings to, your favorable view, you can save it. Next, we have object settings, which we'll come to in a second, where we have already created some objects and how we get there. They can then be, again, also displayed or not displayed, but I'll explain how we get. And further to the right, that's why it looks quite complex, but you can collapse everything so that it's not convoluting the view. We have image analysis tools. There are different ones. There are recipes, enhancement, some charts for looking at data, and the pixel classifier. So we start with the pixel classifier because we talked in the morning session about the machine learning, and I explained that we use machine learning to do the pixel classification. And here we can see different options for the pixel classifier on the right side. So first one, always check your input and training data. So we have a 2D image, the histology image for now. And at the moment, it's set to train on the red channel only. But in order to make it more accurate, let's say our task is to recognize those, say, nuclei, or those cells, the little bit darker ones in the whole tissue. We would like to train on all the 3 different channels because we have red, green, and blue. If you have fluorescence, you can specify the channel you want. So I press 1. It adds the green channel, the red, the blue. So we have all 3 channels. And now whatever I mark in the image as annotation takes into consideration those 3 channels. Okay. Then we can collapse this because we set everything. Then we have different tools on how we want to annotate our image and what we mark. And down here we have the classes. When you start it or create a new classifier, it always creates a background and a wand. You can change the name of the wand and click on it and say, I call it whatever, cells or neurons, dendrites, vesicles. So you can change the class name and you can add multiple classes. It always needs 2 because it needs to differentiate one versus the other class. So you cannot have only one class. You can have multiple ones, but 2 is the minimum. Okay? Then we have confidence map, which I explain in a second, and then what the output is, or if we want to remove the class. Also to the machine learning part, if I click here on this little wheel, it brings up which teaching features we want to use in our random forest. So I explained the random forest of a decision tree that the machine learning is doing, classify the pixels and put them into either our cells class or into the background class. But it takes, for example, here not even the original image. It actually takes a Gaussian blur, Hessian, and differential of Gaussian, and different filters that are applied to this image, and then it's looking at the annotations on our class on what it is using. And you see we have multiple ones. There are a few pre-selected. I will leave them, really pretty good. And if you want to know more on which one each is, that's why now it's resizing. I have brought up this wiki page. So here you can read what everything is doing. So what is the Gaussian blur doing to filter, doing to the image? And then by using this one in the machine learning random forest, how can it change the result? Right? And there are multiple ones. There are some that we call 0 order, 1st order, and 2nd order. Right? Where you're not only creating a filter for the Gaussian blur, but actually a difference of Gaussian and so on. So it's building on top of each other. You can also Google Laplacian filter, for example, and yeah, just Google it and you see, just what it's doing and how the filter would look like. But in summary, those are the features that we allow you to change. I would not change them if not necessary, is my recommendation still. Okay. And then we have a kernel size. So this is how far away from each pixel it looks around. I mentioned it's not only looking at the pixel itself, it's looking actually in an area around the pixels in the filtered mask to determine should it be in one or the other class. And you can set this the kernel size and how far it should look. And there's also a description on what happens if you use the large versus the medium and the small kernel. So usually I don't change it, but those are the options you have to influence the random tree that we use for the machine learning. Okay. So let's go back to the image and actually try to go in. We want to do. It's not too laggy. Let me do resizing one more time so that we see. First, I would recommend you can do it either way. So either you click on the want or the cells straight away, or you first annotate the background. I prefer to do the background first and then basically kind of subtract the want or whatever I want to specify in the class round. So I draw around a certain region in my image. Very simple. Might be hard to see, so that's why you can change the color. Take something like blue. Yeah, should be better with this. So now it's recognizing everything that I marked here, all those pixels should go in the background, but it's not true because we want to have some parts of those marked as our cells. So I change from this tool, which allows you to draw a region of interest, to what we call the brush. You have then this circle, but it's very large. So use Control Shift mouse wheel. Okay. Make it a bit smaller. And then you mark in the background the cells, or basically the pixels that should not be background. So those, maybe those, a bit laggy for me. So this one, this one. Okay. And it should be it. So now we have marked a certain area in our image as background and as want or what are my cells, so the second class. And then you have this little magnifying glass at the bottom. And as soon as I click on it, it will run through a mini random forest machine learning and will give us a preview. So it's now saying generating a preview, and it's done. And this is super quick. I clicked on it, not even 2-3 seconds. It already created a preview of what it thinks should be the cells based on my annotations. Okay, so if I take off the channels, fortunately we have 3 here. This is now the mask. Let's call it the mask. It's a preview mask. Oh, sorry. She accidentally annotated the image. Take it off. As soon as I take it off, it changes again. So it's an almost instant creation of a mask on what it thinks the cells that I want to identify in my image should be. It's not perfect, not completely accurate, but this is the first step. It's also a preview. So it didn't run through the full machine learning random forest to create what we call those objects. Okay, but it's very quick as soon as you click on it. And now we can actually turn on the different channels again. And if you think, maybe not accurate enough, you can always go back in, say here, probably I want to have those pixels too. And that changes almost instantly the preview to make it even a bit more accurate. And by that, you can either subtract a bit of more background or mark annotate your cells you want to quantify. That is really cool. But at this moment, it has not created the confidence map yet. It has only created preview. So very small. And you have, let's say, 4 different things you can have as an output. So one is the confidence map. And this means it's creating an additional channel, a map with saying the pixel intensity of this map mirrors how confident the algorithm is that this belongs to your cells class. Okay, so we will see this in a second because there are already additional channels here, tissue nuclei. Someone labeled them when they provided this data set, and basically it created the mask on how confident it is that this is a nuclei and this is a tissue. You can also have a masked channel straight away. So then there's no, it's almost a binary mask where it's saying this is what we see in the preview, is this is what I think should be the 2 classes. It can do automatic segmentation. So if you click on that straight away, what it's doing is actually creating a preview. You see this now. It's creating the preview mask as well as segmenting each and single nuclei as an object. And this takes a bit longer, and it can be a bit more laborious to identify the cells with the machine learning. So, meaning you can do a 2-step process. First, you create a confidence map, and you use this confidence map then to identify the single job objects or segment them. You can also combine it in one algorithm. If you do this here, then there's segmentation and smart segmentation. Differences in how the parameters influence the segmentation. I prefer to do 2-step, to first see the confidence map and go from there. But you can give it a try if you play around with the software, if you have the access, what it's doing. Okay. So let's then just press teach. So now it's actually taking the GPU, it's teaching a machine learning, it's already done. Actually, that was it. So it created the random forest for this image and the algorithm. And if I press apply now, it creates an additional channel, which is now called cells. My colleague who did exactly the same exercise before, we can open his, created this one. Right? He did different annotations. So that's why maybe he marked a different region in the image. That's why he gets a different confidence map. But it's basically an additional channel. If you hover with your mouse over the cells, it will show you down here in the bottom pixel intensity. The confidence map is always an 8-bit channel. So it goes to 255. You know, this is the background, black. And then we have those objects here. And basically, the higher this value in intensity means the more confident the machine learning algorithm is that this belongs to your class. Okay, this is his things. Looks actually pretty good. Sorry. Actually, I accidentally clicked. Maybe. So. And this is mine. You see my mask here at this area of the image is maybe not as accurate as this. So here are some pixels that have a little bit of value, but they have a low confidence of being part of this mask. Okay. Just I throw it into the chat or the audience. Is everyone kind of understanding the concept for now, how we work? So how we use machine learning to create a confidence map channel. If not, please put a question in the chat and I try to explain it again, but this is how it works quickly. And you saw it just takes seconds to do. But let's look what my colleague did. So this is his confidence map. So he did a slightly different. Can change the color. bit better job down here to separate them. And he also created a additional other class, which he called the tissue. So when we look at our image, you might want to first identify what is the tissue and what are those nuclei inside there. So he actually also drew a region of the tissue and marked the nuclei as this is what I not want, so as background. And he came up with this confidence map. That's pretty awesome. It's actually recognizing the tissue, but not the nuclei and not the white background here. So if you overlay them, it fits pretty well together. This is just done in a few seconds, a few annotations, training random forest and letting the system recognize. So at this stage, we have only created 2 channels, one for the tissue and one for the nuclei, but we have not segmented the objects yet. So that's why now we could go into what we have here, recipes. Maybe go to cell count. There are different ones. So we have created some for wound healing, filament tracking, neuron tracing. Sorry, cell proliferation, cell count. Those are now not machine learning tools. So this is the classical way of we have now a data, we set certain rules. Based on those rules, we will do the segmentation of those individual objects. Because we have now created an additional channel just highlighting the objects we want. And I mentioned before in the pixel classifier, you could do the segmentation straight away. So my colleague, if we go to the object setting, in this data set we provide you, he also did exactly this, where he now segmented each and single object we found into separate ones, right? Into individual, clickable, measurable object from the nuclear mask he created. We can do the same. So this is ours. This is our confidence map, right? And I can now say, okay, not doing machine learning. I just want to quantify objects or detect objects here. So we would go to a recipe. We don't need to remove the background. Skip this. This is our confidence mask. So the higher the value, the more confident the machine learning is that this is a cell. So let's say we set this as 200. We fill the holes. We don't need a smoothing factor for now, just show it. We say object size. Well, it's around 5 pixels in length, maybe some of it. So everything that is between 3 and 7 pixels should be separated, and then it's the separation factor, maybe 3. Here you can again click on the magnifying glass. Sorry. And now it creates a channel, but it's creating it the other way around. Previous a detection channel, so I did an arrow. In the input, I have to tell them which one do I want to use. I want to use the cells. So this channel. So it's creating. It gives a preview. Those are the pixels it's recognizing in my mask. But I'm not doing this on the full image. I'm doing this only on the detected machine learning parts, and you can then optimize. Okay, density threshold. Maybe we should put it down to 250. The larger, the more pixels it will include counting. It's a preview. You can also check the splitting. And if I press start, I don't do this now because sometimes it takes. It's then creating single objects like this. Any questions to that concept? So we take a H&E 3-color channel, red, green, and blue. We mark our cells with annotation. We let run the machine learning. It gives an additional channel, a confidence map with pixels highlighted where it is confident enough that this should be my cells class or nuclei class. Let's call it also nuclei. Franco. The other ones are for my colleague. Right? This is our mask. And then we separate them into single objects. To finish this now, to say, okay, Franco, the task was to identify the nuclei in my tissue. I want to know how many there are, and maybe what size they have, or all the information, like what pixel intensity do they have for the red or in the green, like in the original image. For that, you can go down to the spreadsheet, this last part, where it's away. You have a table of all the 2081 objects it has found. So those are in all each individual nuclei. We get the area, circularity, what is their intensity in the different channels. And if you click here on the measurements, we can have lots of parts that we can measure about morphology, intensity, the position if you do tracking, where's the center of mass, where's the centroid, and then do a nucleic. So, and you can then go in here and it's interactive. So it finds an object. This is what I find really cool compared to some, let's say, open source software that's out there. I click on my object, this one or this one, and it shows me in the table, highlights in blue, which one it is that I'm looking at the moment. And if I go to the chart, I can now plot even, let's say, area, which is basically the size, and then parameter, or let's maybe go to circularity. And I can mark them like in a dot plot. I'm not sure if you're familiar with flow cytometry, but this is a dot plot. Each individual dot represents an object. And here we have the parameter we measured, and you saw we can measure quite a lot of them, I think 50 different parameters for each single object. And then we can highlight and say, show me all those that have, let's say, let's do it the other way. Only show me the large one that have a large size. And then it's highlighting them in the table, as well as this one, this one, this one, this one in the image. So it's pretty interactive here. What is there? You can export all this to Excel. So my recommendation is, if you use the software, especially the AVR web version, you do your analysis, you save your TIFF file as AVR TIFF. By doing that, it creates a TIFF file that has the additional channels in it. It has the objects in it. It has the measurement data in it. So that's why when we open it, this was already there. Okay, so my colleague already trained the machine learning, created additional nuclei and tissue channel, the same as I did. I showed you how we do the annotations. He then segmented those objects into the different nuclei, and all this is saved in one AVR TIFF file. So that's the one we process. Yeah, so that's I think. But if you want to have only the data, you can click down here. It's export to Excel. Ask you which parameter do you want to Excel, CXL or a CSV file, and you can export them. So then you also are safe. You can also save the pixel classifier. I go here. It's very important. So because my colleague did different annotations as I did, his confidence map looks a little bit different than mine. The more I do the annotations for the different objects, I can make it more accurate, less accurate, depending on what I'm doing. But I can always then save the classifier. So after I have taught classifier, I can go save classifier. And now I can do actually batch processing. So I can feed in, I don't know, 10, 20, whatever amount of H&E statings and tell the system, please apply the same machine learning random tree forest to all those images and create either straight away the segmentation or those confidence masks. So then it will go through, let's say, all 10 images. All 10 images will get an additional nuclei and maybe tissue channel. And I can do a second batch on top of it and say, okay, now segment the nuclei into separate objects, and please give me all the Excel files with a summary of the data. Okay, so you can save the machine learning transfer. And for publication, it's another one point. So if you then want to use this pixel classifier, and it's the final one where you have done all your analysis, you created your charts, you are ready to publish, make sure that you also take this one, which is copy all training fields and training data into one spot. So what it's doing here now is, if we have, for example, a Z stack, I come to that with 10 Z stacks or 10 Z planes, but you do your annotations in 2-3 of them, so not all of them. It saves also the images on which you did the annotation and what you annotated. That's why you can show the reviewer, this was my data set, because you always have to provide the data set. But those are also my annotations that I use to train the pixel classifier. This is the pixel classifier. So everything can be saved, and it's in the format to be used also for the review of some publications. Okay, great. For the means, any questions in the chat or to me directly for the pixel classification? So this is one.
No, Franco. There are no questions in
Okay.
the chat box.
Perfect, thank you. So this was the first concept. Let me close this image on how we get from, just a little bit slow, I apologize, but it's because I'm also the one who's the objects off. And then how we go from this image to within just small region of interest, few annotations. How do I get my objects? And I don't want to have the whole tissue. I only want to have my nucleus very quickly. So this was one exercise you could just redo. Access. Let me move this away. This is an example of it's already pre-analyzed. If you open this one up, it's called object cell analysis. Now this is 3D. So we give you this 3D Drosophila data set, has 125 Z planes, so 1,200 by 600. See the different Z plane. If you then go up here, right between edit and view, this is little simplifying class. If I click on that, it jumps straight into the 3D view. So now we can round our sample, look at it. We can again work on the histogram. There's only one channel for one. Actually, this is another data set which is called 3D cell analysis. Interesting to look at. Also provide this if you go to open files. The data set is a little bit larger now. It's 300 Z planes, but the image as such is smaller, 300. You can go through. But we use this one to show you some of the relationships between the cells. See this. Just in the fourth channel. This channel intensity you can remove. So also here in the view, we are now in the 3D view. Let's take this one. So here, showing straight away, we have, let's call them vesicles or cell membranes, and then we have the nuclei. It's rendering them straight away. Okay, can back. Or it's centering it again. And yeah, so we have then those recipes to quantify what is a cell, what is a nuclei. Nothing to do with machine learning or deep learning yet, just want to give you an idea on how everything would look 3D. So you still have your display settings for channels, for example. And then you have the display options. You can do some plain clipping and so on, but run out of time if I show you. There's a 3D data set. And here, my colleague did already the analysis on the different channels, the rendering. Now, this is an example where we used pixel classifier, create some masks, or we use directly the signal that we have from the channel. And then the software can show us, okay, what are the cell membranes? What are the vesicles? They are marked in different channels. So just want to show this as the power of this software that it's very easy to navigate around. I'm not sure if you're familiar with Imaris, Revis, Amira. It's probably similar, but the visualization is very simple. So as soon as you have the objects, turn them off, turn them on, you can change the color. So I encourage you, if you have the software, just play around with them. Let's say, take everything off here. So those are the nuclei. For example, you click on the color. I want to make them in green, and whatever. So those are the display settings, which I really cool. Last one would be how the pixel classification would work now, let's say in 3D. So coming back to our Drosophila, it's 2D. This one off. So we have our Drosophila. And even if we now go into the pixel classification, so I encourage you also to open this one, 3D object analysis with results. So those are the results, but click away the results. You don't see them. It's just what it could look like. In order to now do the same as we did before, we need to create an additional. It has still a 2D pixel classifier in there, and we need to create another one, a 3D one. So it recognizes if you have a 3D stack, but you have to select it because otherwise it's using the one that we had created before for the H and E staining. We check the input channel. This time there's only one channel, this one. And we do the same thing. We mark this area here. Change the color. So this is red. Then want, well, again, I want to have those cells. Increase my brush a bit. So, let's say it's part of the cell. This one. This is also a cell. Start with this. And you see in the preview, it's already creating what it thinks should be the different levels, or no, the different objects. Okay. Around. It's okay. It's not the full machine learning yet. It's just a preview. It's very quick. And you can also go to a different Z plane, and it almost instantly recognizes them. Can then either continue do the annotations. 3D all gets now a bit slower. It also asks you, can you please apply? So everything that comes red here is kind of not an error message. Sometimes it's also a suggestion which says the smaller region would speed up the preview. So there we could go onto this little button, which creates a region of interest. Here we have now region of interest. Let me move this in. When we go to the pixel classifier now and ask it to look at the region of interest, hope you can see it. Sun in the background. I can now tell the preview and the machine learning, please, if I tick this box here, please only use the region of interest for now. So it's not previewing the rest of the whole 3D stack. In this one, it's still fast enough, but you can check your own data. The larger the data get, you might want to do the preview only in the region of interest, just to be faster with your annotations. For example, here, say, okay, let's go through the Z stack. It's actually pretty okay. This comes to a question on how many annotations you should do. You saw we did basically one region and a few cells in the 2D image before, in the H&E image. Here we have now a Z stack. I would recommend to then, it's pretty okay. The more dimensions you have, the more annotations, maybe a bit more. So we'll go through. That's it. And we would now then teach pixel classifier, that was it. And then apply. And it's creating confidence map. And you see here, it was really quick. It was just seconds, almost instantly. But we only focused on the region of interest that we marked. And again, this speeds up the process. As soon as I would go down here, tick it off, I can now apply the whole machine learning and random forest on the full 3D stack. Okay, I'm not doing it because sometimes it can take, you know, a minute or two. The larger the data set is, the more planes you have, maybe even time. Despite we are using the cloud computing power, can take some time. So that's why we will see the results though. So this is again what my colleague provided. So we created the confidence map, and now we created the objects. Started everything in 2D in a region of interest, but then we applied it to the whole stack. And if we go into the 3D view, see our region of interest down here, which we can take off. We can take off the original channel. And this is how we detected it. So we use the machine learning to classify the pixels and what is background, a few Z planes, you know, take one at the beginning, maybe in the middle and at the back, teach the model, apply the model, and then you can start the segmentation using your one channel, which is a bit more cleaned up than the original channel. So that's the whole idea for this segmentation. See, it's all. You can then go to the spreadsheet. As soon as we have created the objects in 3D, is the same as before. We now, you know, see the surface area, but we also see the volume because we created the objects, and we can have the different intensities from our original channel. And again, we can go to the plot and plot, you know, surface area versus the volume or any other measurement that we have done. We can also highlight them again, dot plot, and then it will highlight them. See. So the ones that are in white are the ones that are currently displayed. And then we can also look look at those. Any questions to that? So the same principle applies that we have done on 2D and 3D. However, please note pixel classification. Let's switch back to 2D. Pixel classification, despite we are using a what we call 3D pixel classifier, we are still doing in 2D on a few different Z planes, okay? To create a confidence map or the segmentation then on top of it. So original channel, this is our confidence map. You see background is a lot less like this. This is our original channel. So we helped to clean this one up, and then we did the segmentation on those for the different objects. Okay, how much time do we have? 8 minutes left. Okay, let me just show you one example, which is also provided. Let's close this one. Which is this one. This is a neuron set. And we can go through. The set has 233 slices. And second. That's how it looks. Yeah, so here. So here's the neuron with the soma in the middle. We have the dendrites and we have those spines. And my family just came back. You might have to give me a second. If you hear some noise, let me know. Yeah, interrupt my thought. So apologies. It's the home office. So we have the neuron in 3D. We move around. We have already provided you some rendering object detection. As soon as I take this one out. Today. Okay. So now this is the rendered. Let's. I want to see the spines in red. Okay. And the soma in yellow, just for the different. Okay. So we rendered the soma. We detected the dendrites, and we detected the single spines on those dendrites. And I mentioned we have now all those objects, which we again can look at. Sorry, it's just very slow today. You can choose the set, and you see all those information for each and individual spine that we have detected on, what's their length, what's the volume, what's the ratio, which branch angle are they sitting on. So all those information we have for each and single spine that is on this dendrite. And if we go up here, I encourage you also to note this one up. It's called a classifier, but now we are not classifying the pixels. We have already found pixels and the classes and rendered them, detected the object. We now do is we want to create a classifier using machine learning on the different spines. So now it lists us, it has 261 spines found on all those dendrites. And we can now go in and click either, let's say, in the image, let's say this one, just pick 3 random ones, this one. We want to assign them to a new class. I call them normal spines. Okay, so those are the 3 we marked before. This one, sorry, this one and this one. I assign them to this class, and then I click in my image, let's say the other ones, this one. So, sorry, this one. and we assign them to additional class, which we call abnormal spines. Assign them. So we have now 3 examples for the normal ones, 3 examples for the abnormal ones. This data set is not very strong. You see a little bit of red here. The more you provide, the better it is. We press again teach. It's now training the classifier and then apply. Okay. Yeah. So it has applied now from this learning that I did. So different objects. It can be spines, it can be vesicles, can be nuclei, can be different cells, whatever you detect as objects before in the machine learning. You can then use the what we call object classifier up here. If again some training examples, you can provide more, you can take some out, but down here it now created 2 groups, which is those are the normal spines, those are the abnormal spines. Apparently it hasn't done it completely perfect, so I have to check because I probably duplicated some of the spines in the selection. So theoretically, it should work that you have then 2 groups where the machine learning not only classified the different objects we had into the different groups. Okay. So you don't have to go through all those measurements and see where are they similar. You let them first find them and okay. I think we are up with time now, so I would stop here. We planned for an hour. I think it's a lot to digest for now. Are there any questions from the audience?
No, Franco, there aren't any. But if any participant want to ask, they can unmute themselves and please go ahead.
Franco, Sachin
Yes.
here. For the benefit of everyone, if someone later on wants to try out their own data, how do
Yes.
they import the data into this software?
Yes. So for this one, what we actually have to do is this is the second one. So if you log in, you have the AVIA here, and the second one is what's called a CyberDuck. This won't work now because I'm not in the VPN. So there's a description. Okay, let's say it this way. If someone wants to try, let us know with their own data. I provide the description because you can open a connection here. And then, for example, I can link my Google Drive. Yeah, so you cannot just easily upload it to this virtual space here. Basically, you have to link your data that you have you sitting somewhere else. This is one caveat. We are working on that. There will be a new development coming. You can actually upload it and store your images. At the moment, you have to store them somewhere else. So I have a Google Drive. I would enter my, I'll say connect. It will now open my Google Drive. So I will log into Google, and then it will provide me with a code. And I use this code to enter here. And then it connects, and then I can basically upload the data from my Google Drive into this. Sorry. Into this temporary folder. Okay, I should have done it to show you. So sounds complex at the moment. Is just because we are using the Amazon. We don't have the storage space yet to upload. This will come. Should I just say it as it is? At the moment, we will link with CyberDuck any storage place that you have, OneDrive, Google Drive, Dropbox, and then it will pull, you can specify it on, you pull the data from, let's say, your Dropbox into this temporary folder, and you can open it. Also, one question that often comes up is what files can we open? These are the formats that even it's cutting off it quite a lot. So everything that you can open with, for example, Image2Numbers, we can open too. So we can not only, like our files, you can also open the CSI from Zeiss, Nikon, Olympus, some of the new i5 light sheet data. There will be a short version where it's temporarily transferring the images. So when this AVI is created, actually, or the software draws back onto the open source from Image2 to open your images. So I have not come across a format yet that we could not open. Not saying it can do everything or all the formats, but it should be quite a lot. It does not need to be TIFF. I still recommend you then, if you open, let's say, your a live file, and you work on the data, you created your pixel classifier, you created your object, to save it as an AVI TIFF, and then download it from this temporary folder back into your Dropbox. The reason is, as soon as you close the session, your data is removed because it's shutting down the virtual machine. It's basically shutting down the computer, and by that it's erasing all the data. Okay, does it help?
Yes, Franco, it does.
Perfect, thank you. I hope it's okay. I apologize again if we could not have the participants to join. Reach out to the organizers, reach out to us. We will definitely get it working. We might provide even a full license. I mean a desktop version, not the web version. If you put that one with a license key for 14 days, should have worked. I will follow up with my colleague. For that, I apologize.
No, not an issue. So I'll request all the participants to check out the software once. They can also upload their own data and analyze and see. So if there are any questions regarding that, just either directly contact Dr. Franco. He has provided his email address in the chat box, or you can contact us and we will relay the messages to him. Thank you, Dr. Franco, for joining us and giving such an insightful presentation and overview of the software. We'll definitely try.
Perfect.
So I will request everybody to switch on their video so that we can take a session screenshot.
Perfect. Yep. Start the video. I might be dark in the background. No, works actually well. This is me. Sorry. Yeah. Hello, everyone.
Yeah, we are done. Thank you so much for joining.
Perfect.
Thank you,
Thank you for
Sachin.
joining. Any questions, let us know. Bye-bye.
Sure.
Thank you. I have also shared my email address in the chat
Thank
box,
you,
so
Sachin.
you can reach out to me as well.
Yeah,
That's
sure.
a local colleague. Yep. Perfect. Bye-bye.
Thank you. Bye, everyone.
Thank you.